Okay, so let's look at another question. So this question that we have now is from Oguhle Nompilo Dube. And Nobuhle gave us this question. So let's just read and we're going to scrutinize. So 10.1 is also question 10. So you can actually already see the trend. It says the diagram below shows different positions A, B, C, D, A of the coil in a DC generator. Now we know we're talking about direct current, and to make a direct current, we have to have split rings and not slip rings like the other one. Generator, I know it's mechanical energy. I must first work before I can have electricity. That's the energy conversion that's going to take place. Now that's for a complete revolution. When you talk about a revolution, that is an entire rotation. So the coil is rotated clockwise, meaning it's moving in this direction at a constant speed in a uniform magnetic field. Obviously, when you talk about generators, you need to have a magnetic field there. So this is the direction of the magnetic field. So in this case, they don't actually give us the magnets, they just give you the magnetic field, which means if ever you came to a question where they said, in which direction is the current moving, then you have to make sure that you move your fingers in that direction because the arrow is moving in that direction. Remember, it must always point to the south. So this is how it's turning. I can see, okay, it's rotating, and then so it starts at A, rotates all the way around, and it comes back to A. Now remember, if a coil is rotating in a magnetic field and it's rotating and so forth, it becomes a maximum or a minimum in certain points. Remember, we wanted to actually have or get most of the magnetic field lines to actually pass through it, right? So that's already, I can see that is what's happening there. So let's look at the first question. So 10.1.1 says we must write down the energy conversion. Again, we must write down the energy conversion that takes place during the rotation of the DC generator. And this is also then again for 1 mark. Let's just go back to this one. When we talk about a generator, we must first put in some mechanical work and then we can have electricity. Whereas a motor, we can just plug it in, easy technology, just plug it in and it does all the work for you, right? So the energy conversion for a generator is mechanical energy into electrical energy, and that is what the examiner is looking. And as you can see, question 10.1.1 is exactly the same question as the other questions 10.1.1. And I can see that this question was actually, I think it's November 2018, and the other one was also, I think 2000 and something. So let's write down the first one. So the first one I have 10.1.1, the energy conversion that takes place is from mechanical energy to electrical energy. So that's the first question that we have. Very easy, you can't get that wrong. Now let's look at the next one. Now it says we must sketch. We must sketch a graph to show how the induced EMF of the generator varies with time and clearly indicate A, let me just take that off so that you can actually see if you are writing this down. So clearly indicate A, B, C, D, and then A on the graph. Now, very important word is sketch. Remember guys, if they say sketch something, it means a ruler and a sharp pencil. Please don't go freehand, it's not art class. We want to see consistency, right? We're all about having it neat so that examiner can see that even though it's not drawn to scale, but it needs to look neat and it needs to be consistent. No freehand. You need to have a sharp pencil and you need to actually have a ruler. So we need to sketch this, and as we are sketching it, we need to show the rotation of the coil. What this means is, as the coil is standing in this position and it rotates, we're going to show it in a different way on the graph. Remember, when it's actually rotating, we can actually even use 0 degrees, 90 degrees, and so forth. So we can show that. And then again, we also need to remember to know whether is it DC or is it AC. So let's see how we're going to sketch that. So I can already see that here it's moving. It's actually up, going flat, it's perpendicular to the magnetic field, parallel, perpendicular, and so forth. Now, then I need to remember what my teacher taught me about the vertical lines in a magnetic field. So this is 10.1.2. And now I remember that this is a DC generator. Just to go off topic a little bit, if you're getting confused with which graph works, for example, if we talk about an AC generator, draw your A is always above, move this, that was your A, then you can take that off. AC means alternating, so it makes the sine graph. When we talk about DC, I'm going to draw my D, but I'm going to draw it the other way around. Then I'm just going to put another D like that, right? AC, it must make a squiggly line. D must have 2 humps. So if you are getting confused, always remember this method of doing it. So now I know that it's DC, meaning I'm going to have 2 bumps there. So let's see how these 2 bumps are going to work. Remember, now I can't use a ruler, but you must use a ruler. Make sure that you draw it nice and neat because they do say sketch. It's DC, so it's going to have 2 bumps that look like that because it's direct current. And then they say we must indicate the rotation that occurs. So now remember, if we're looking at A, it is perpendicular to the magnetic field. So we have perpendicular, perpendicular, parallel, parallel, and also perpendicular. So remember, when you are sketching, I think I just want to add this. Remember, if you are sketching DC or AC and they're talking about a complete rotation or a revolution, in your head, always have a circle. What this means, let me just make an example. If it's DC and we have the 2 humps like this, if I was to move this hump and put it there, it gives me a circle. If we have AC and it's alternating and I move this one and I just flip it over or reflect it, it'll give me a circle. So that's what revolution means. You must get a circle. That is a complete rotation. That's what the examiner wants to see whether you know. So now we have to identify the different positions. So now remember, A is actually standing upright. So this will be A because this is at 0. Now remember, when you have your circle, always split it up in half with a dotted line like this and another dotted line like this, like that. And then when we get to there, it's usually the beginning of it all. So this then again will be A. So this is B when it is parallel to the magnetic field. This will then be position number C. This will be D, and then this will be A. I just want to go back to this graph here. You can see A standing upright. The magnetic field is coming in this direction in this case. And then it's going through. It's coming in this direction, parallel to it, perpendicular to it, and so forth. And another thing to remember, when we have a complete rotation, we start at A and we must end at A. If you do a cartwheel and you are going and you're flipping over your hands and you do a cartwheel, woo, you don't land on your head and you stay on your head, you come back to your feet. So remember, the same as a generator, wherever you have started, you need to end there again if it is a complete revolution. But just like on the top of my head, examiners also like doing this. They might just like spicing it up. Let's say, for example, they had given you a graph like this. They had given you a graph like this, and then you have the 2 humps like that. And then they say you need to place this A, B, or C again. It's exactly just as that. You can just, again, start it there. A is there, and then B will be there, and then this will be C, this will be D, and starting there again, this must be A. So they can either give you one like this. Don't let this part confuse you or fool you. Just name and number it the way that they have given you, because they said they started at A. They didn't start at half a rotation. They started at A, so A must be there. So sometimes the examiner wants to spice it up because they think you don't understand, but always look at the diagram. If they started A and it wasn't half a rotation, it was actually standing upright, then you must start it upright, even though they're trying to confuse you. So that was then 10.2.2. So now we've sketched it. Remember to use a sharp pencil and a ruler, and that was for 2 marks. And then we have a mathematical calculation. Now we have a small AC meaning alternating generator, meaning mechanical energy to electrical energy. That is the conversion for a generator, and providing an RMS voltage of 25 volts, which is connected across a device with a resistor of 20 ohms. The wire connecting the generator to the device has a total resistance of 0.5 ohms. Now this is the diagram that we're given, and I just want to make that in color. That is the wire that we are given. So the first one, only for 1 mark, says write down the total resistance of the circuit. And now they've actually given us, they're telling us it's connected across a device with a resistance of 20 ohms, of 20.5 ohms. So I'm going to add this one and this one together because we have a device and then we also have a wire. So that's very easy. It's for 1 mark. And that is 10.2.1. So I'm going to add 20 ohms, which I'm going to add to 0.5 ohms. Okay, we can really do this from the top of my head. I'm going to get 20.5 ohms. That is the total resistance of the circuit. So now let's look at 10.2.2. So in this question, what they're asking us is, let's see, they say we must calculate the average power delivered to the device. And this is for 5 marks. This is actually a lot. So let's see what we have. We've got my RMS. let me write it this way. I've got my VRMS, which is 25 volts. I've got my resistance that I just calculated, which is 20.5. And that is my wire, and then we are looking for the power. So then again, very simple. Just go to your formula sheet, choose the one that you can actually use. But like I always tell my kids, choose a formula where everything that you can plug in, you actually are already given in the scenario or in the diagram. Do not go and calculate something on the side and then you plug it in, just in case you get that wrong. And then everything else makes it wrong. And you are showing the examiner that you don't really fully understand what's going on. So we're trying to avoid that. Choose a formula where you can just plug in everything that you have. So let's see. For this one, we are looking for the power. So now I can actually use the IRMS formula and my VRMS. So I can actually find my current first, because I do have RMS and I do have my resistance. My VRMS, I'm given in the scenario, it says it's 25 volts. The resistance that I have is this one, and it is 20.5. Now, if you didn't get this resistance wrong, make sure you substitute this resistance, whatever answer you got there, back in there. You will get it right for continuous assessment, even though this answer is incorrect. So make sure you substitute it correctly in there. So let's see what my current will be. Remember what I always say? Put brackets around it so it doesn't do BODMAS. So we've got 25 at the top, and at the bottom I've got 20.5. Oopsie daisy, 20.5. I want that as a decimal, so I'm going to make that 1.22. I'm going to round off this, so the 9 will change the 1 into a 2. Remember, anything after the 1, if it's 5 and greater, it will change the number. So I'm going to get my current as 1.22. Talking about, even though it's IRMS, it is current. When we talk about current, we measure it in amps using an ammeter. So now I've got my IRMS. And I know it's right because I was given this one, and this one I had to calculate, but this one was pretty obvious. But now I need to find my power. So I'm going to work here on the side. So I can say PAVE, which is power average, my RIRMS, that is squared, and then I can use my resistance. I'm looking for my power. Now, my IRMS, I'm going to take this one here, 1.22. Remember, it's squared. My resistance is 20. Okay, let me see that I don't make a mistake here. I think we need to first find the power. We need to first find the power between, because it says average power delivered to the device. So I need to calculate the power of the wire and then the power of the device and then subtract the two to find the average power delivered to the device. Okay, so that I don't get confused there. So for this resistor, I'm going to use the resistance of the wire to find out how much power is this wire actually using, which is 0.5. I know though that the current will go through because it's actually a series connection. So let's see what we get there, because we're looking for the average power that is actually being delivered. So I'm going to have 1.22 squared. So I'm going to write it there. And then I'm going to have 0.5 because I want to find the power for the resistance first. So I'm going to get 0.74. The 4 is less than 5, so it will not change this 4 into a 5. So I'm going to get 0.74. And the power, remember when you talk about power, it needs an SI unit. It is a capital W. I'm going to work here at the bottom. Now I'm going to find the other power for the average power for the device. I'm going to say VRMS, RMS, that is squared all over my resistance, because that is the information that I'm given. My VRMS is 25. I'm going to say squared. The resistance of that device is, the total resistance is then 20.5. Let's see what we get there. So unfortunately with this one, we had to do it separately and then bring everything in together. So I've got 25 here squared all over 20.5. And then I get 30.49. The 7 will change the 8 into a 9. Anything next to the 8, if it's 5 and above, it will change the number. So I'm going to get 30.49. And when we talk about power, it needs an SI unit. It is a capital W. But now they're looking for the actual power, right? So I've got this power and I've got this power, which I'm going to subtract to actually see how much is then the actual power that's required. So I'm going to say 30.49 minus the 0.74. Okay, no, I can't do that in my head. Let me use a calculator. I'm going to 30.49 minus 0.74, then gives me 29.75, exactly to 2 decimal places. So I'm going to get 29.75, and that is then power, meaning we need to have a W there. So let me just see if we just answer this question. We must calculate the average power delivered then to the device. Yes, because we had a wire there, which had a total resistance. We had another device. Yes, so then there we are. Then that is all for 5 marks. And remember, when the examiner is actually marking this, you do get a mark for you for actually having all the formulas and correct substitution. And it's actually easy, 5 marks and then all in the bag.